Dear honorable guests, sponsor, SPE Thailand members, ladies and gentlemen, welcome to our SPE Thailand monthly meeting. Please let me introduce myself. My name is Savarin Blicklen, or you can call me Annie. I'm very honored to be your MC tonight. In 2023, we continue with our mission to keep you informed of what's going on in our industry and make new knowledge available to you with monthly technical presentation. And tonight, it's our honor to have Kun Edmund Leung to share us about non-intrusive well and reservoir surveillance solutions using chemical tracers for improved reservoir management. Our vision is to be open for sharing information with our peers and across companies so we can provide energy for the kingdom. And of course, we'll be very happy to meet many new faces joining our program more and more every year. Our vision is to be open. And the agenda tonight, we'll have attracting program with a couple of announcements regarding the section, followed by our highlight of tonight, which is a presentation by Kun Edmund Leung. We will then have a couple of closing remarks, and finally our lucky draw. We'll have attracting program with a couple of announcements. And now a few section announcements before we go to our technical meeting, which is a presentation by Edmund Leung. Thailand section valid memberships as of today is over 100 members, combining 339 professional and 204 student members from Chulalongkorn, Suratnari, Prince of Songkhla, and Chiang Mai University student chapters. Not only retained, but our section has also gained 48 new professional members since the beginning of this year. I'm so glad to see 19 renewed members in February. However, we still have around 108 professional members from 2022 who has not yet renewed their membership. May I remind you, so please recheck your membership status, and if you haven't renewed, please continue to do so. As you know that SPE Thailand is still the largest professional oil industry organization where you can regularly meet and greet in a relaxed environment. On the topic of SPE membership, there are plenty of reasons, as you can see on the slideshow, why you should maintain a valid status, and even more reasons to join. I will not go through all of this, but worth mentioning that the key benefits of belonging to one of the most active SPE sections in Southeast Asia are the regular opportunities to network, share knowledge, and socialize with peers of the same interests in our industry. So please be encouraged to invite your colleagues to join our meeting, or even better, join our SPE members. These are the companies who are sponsoring us, our Thailand monthly technical meeting for these seasons. For any of you who may have just turned into this meeting, if you would like to see your company name in here, please don't hesitate to contact us. We appreciate your support, and of course, our society needs you. And now, please let me hand over the microphone to our program chair, Kun Chia, who will do the honor of introducing our speaker for tonight. Please give me an applause. And now, please let me hand over the microphone to our program chair, Kun Chia, who will do the honor of...
Hi, good afternoon, good evening, sorry. My name is Chia. So today we're honored to have Edmund joining us today to introduce this very interesting topic, which I don't quite sure what it is, but anyway. So Edmund is currently the Senior Technology Advisor with RESMAN, and prior to this he was the VP of Technology with RESMAN based in Norway. He graduated with a petroleum engineering degree back in 1995 and started his career with Schlumberger, holding various roles in technology, business development, management, and worked in several countries such as Saudi Arabia, Kuwait, UAE, Malaysia, Indonesia, Australia, and USA.
holding various roles.
Prior to joining RESMAN, his last position with Schlumberger was global reservoir advisor, I believe, taking care of sand management and completion segment. And he co-authored quite a few papers with SPE and is an active member with the SPE. So without further ado, let's welcome Edmund to share his topics. Thank you.
Taking care of sand management and completion segment.
Okay. Thank you, Chia. Thank you for everyone showing up today. It's or this evening. It's quite a large crowd for the SPE. And thanks for the introduction. So yeah, I know the title is a bit long, but it's about using chemical tracers to perform surveillance, whether it's well-centric or between wells in the reservoir. And yeah, without further ado, I'll just start the presentation. Many of you probably believe that tracers, if you've been in the industry probably more than 20, 30 years, that they're traditionally known as, you know, they were radioactive. But now, in the last few decades, it's changed from radioactive to chemical tracers. So they're non-toxic, and, you know, basically they can last for a very long time, and they're inert. Essentially, they're organic chemicals that trace the flow, whether in a pipe, in a well, or in a reservoir between injectors and producers. So one of the, I've got to get used to this, here we go. Yeah, one of the important points of tracer technology is that if you inject tracer in an injector and you detect it at a producer, you're talking about, you know, it's a mass balance. If you detect it, then you know that there's a connection between your injectors. Okay? So it's not like something like if you do 4D seismic, for example, you may be shooting for a while and you're interpreting sound, but that's an interpretation. So you inferred something from a measurement, whereas a tracer is a direct measurement and is about mass transfer of in and out. And the things you can do, what most of you are probably familiar with, tracers have been used for decades to monitor producing inputs. But more recently, it's also been used to monitor storage reservoirs like carbon capture. And I'll talk a little bit more about that as well. So that's more of a more recent application. And also these tracers are often used to define or verify, is my fault leaking? Is it sealing? Does it actually exist as well? Or tracer technology is risk-free because it's operationally simple. And what I mean by that is because you don't need people in the field. You don't need skilled people. And to obtain the data, you just need sampling. So the typical service of most tracer services is that the service provider needs to design the tracer for the well and the reservoir conditions. So it will not absorb to the sand and just accommodate for acid jobs or different chemicals that a tracer may see over its lifetime. There's only really two ways to deploy the tracer. The one that I've been talking about, injection, is just injecting 5 kilos, 10 kilos of tracer through a flow line and into the injection well, and then the monitoring begins right in the reservoir. Now there are also tracers that are embedded in polymers or plastic, and that can be installed inside a completion, like a sand screen or a pup joint, and that's used to permanently monitor a well. So in a way, it can be seen as like a production log, but without the wires and without a tool, because the tracers are permanently stored at different depths along the well. And then after that, to get the data, it's just sampling. The lab analysis to find the tracers, interpreting the data, the different signals that come back. And also that information can then be used to populate your reservoir models or your well models. In general, most tracer services can provide many years of monitoring, and that data is used to, reduce modeling uncertainty. In terms of what can tracers do, I've mentioned this word multi-scale. Multi-scale means that you can measure theoretically less than a meter if you were to run inflow tracers, being separated by compartmentalized by packers and having unique tracers in each zone. And then often used to verify flow. Is there oil, is there water, is there gas flowing from these different zones? And also be able to quantify how much comes from each zone as well. So that's the inflow tracer. These are the permanent ones installed, usually in a new well in the completion itself. There are also tracer services where you can measure the residual oil saturation left in your production well or around your injection well. So typically done if you're going to do a enhanced oil recovery pilot, measure the residual oil saturation before you execute the EOR, and then measure it 6 months later or 1 year later, and just see how much, what has the residual oil saturation reduced. There are other tracers that you can pump during fracking, to pump a unique tracer with the frac fluid. And then the one that I've been talking most about is really the ones that you're probably more familiar with, is that you inject it in an injector and detect it in a producer. And what do you learn? The information you gain is to know connectivity between your injectors, flow allocation, and what I mean by that is that if I inject 100 kg of tracer here and I detect 80 kilograms here and detect 20 kilograms here, then you know which connection is more important than the other. Sweep. So it's very important to understand, especially in a waterflood or EOR, how much are actually sweeping between your connected wells. Because we know the breakthrough time, the injection and the detection time, and also we know the injection rate, we can then calculate the swept volume between the connected wells. So these are simple analytical methods that you can use with the tracers that you pump in injectors. And there's also services to also estimate the residual oil saturation between the connected wells as well. So perfect again for EOR. So this one's about around the near wellbore, and this is about getting the average residual oil saturation between your injectors and producers. And last but not least is storage reservoirs. The main objectives for CCS is to determine are there leaks in your wells or possibly leak through your cap rock to surface. And there are actual case studies that this has happened around the world already. So that just gives you a summary of what tracers can be used for at different scales, from less than a meter to greater than 100 meters to tens of kilometers apart. So I'm going to now focus just on the inflow first, monitoring. This is a typical scenario with subsea where you may be drilling quite a few horizontal wells, multilateral wells, and to access them with a POT, it's a bit challenging, risky, and expensive. So what if you could have sensors from the toe to the heel in every well? Each of these sensors can be these permanent tracers. They're chemical sensors, and once oil, water, or gas physically touches them, they will release the chemical into the oil, water, or gas phase, and of course the flow will transport it to surface, to the FPSO in this case, and you take samples. So each of those samples have many traces, and you analyze in the lab, and then when you detect those traces, you know where the water, gas, or oil came from. So for example, I have a very exaggerated aquifer breakthrough. So suddenly all these water traces will suddenly release into the water phase and go to surface and just tell the operator where, or the subsurface, then where's the water coming from. I also mentioned how much. So there are models and methods to be able to match the data, the tracer signals with models to estimate how much comes from each zone as well. So how do these traces embedded in polymer work? They're embedded in this picture as you see here. You can't see them, of course. They're sub nano, and they could be oil, water, or gas sensitive. They could be embedded in thick fishing wire if you have a very tight screen, for example, like in a premium mesh. But they can just be installed in almost any kind of completion, whether it's open hole or cased hole. And they release through a process called diffusion. And as you see here, if we were to, drop this colored dye, it just diffuses out, right? And they're also designed to only release to the target phase. So it must have oil physically touch it to release into the oil phase, or into water, or into gas. There's also a reason why there can be years of monitoring in this technology. Could be up to even 10 years. So that's because of the very low detection limits of the lab equipment these days. We can now detect down to parts per trillion. And to put that in perspective, that's like taking this droplet of water that could be, let's say, mixed with a bit of sugar. And if you drop it in there, it'll be very diluted, of course, but the machinery can detect it as if you had 20 Olympic-sized swimming pools. Okay, so you could actually have equipment that can sort of, let's say, detect the sweetness in 20 Olympic-sized swimming pools. How to install it in the completion. These are just some pictures. This is a wire wrap screen. So you could have oil, water, gas, all the way around the circumference of that screen. Because the completion guys are going to rotate that completion to get it to TD. So it doesn't matter if it gets rotated. This is actually an installation with a shroud that's blank. There's no perforations. And that's a completion where you can run as a liner, and you can perforate through it. Okay, and then the traces release in a casing cemented well. This is, believe it or not, a fiberglass completion, and that there's a particular well that operator in Australia that needs to run fiberglass completions, and these are a wide variety of completions that these permanent tracers can monitor. Could be steel fiberglass completions, just premium wire wrap screens that could be installed with passive ICDs, check valve, autonomous ICDs, gravel packs, slot liners, multi-stage frac. You name it, they're all there. So they could be installed during the screen manufacturing period, but if you have screens already in inventory, you can just build a pop joint or a tracer carrier, and this carrier would be installed adjacent to the screen. And then they will come in contact with oil, water, gas, and go through the screen and then through the ICD in this case. The cemented liner, just add a bit of OD on a liner, and you just run it like any other liner. You cement around it, and then you just perforate through it, and then the traces flow. When it comes to sampling, there's liquid sampling that I'm sure you're familiar with, and it's all just standard condition sampling. And you just label them, the time of that sample being collected, and then sent to the lab in this pelly case. But gas sampling, there is now a very sort of safe method to capture samples than compared to the past where you would need high pressure gas canisters. In this case, what I have here is a picture of a syringe. You just go to your bleed valve, suck out some gas. It may have traces. You would take that syringe and inject it through this 20 centimeter tube. Inside it has carbon beads. This carbon bead absorbs chemical traces. And then you would vent out the gas. And only chemical traces reside in this 20 centimeter tube. And then it can be just DHL'd to a lab. So it's a very simple way and very safe way to transport a gas sample. And then, the lab will then, of course, then find the traces. So let's go through some case studies. This is a simple water breakthrough example. There's the SPE paper about it. It's an Australian operator that in a subsea environment, they had they just ran 4 unique traces in each well. And you can see that, think of this as concentration axis, this is water cut axis, and the water cut measurements coming from a multi-phase meter. You got each of the colors represents 4 different concentrations of water traces. And you see they're very stable. So there's some water, but it's not increasing. Talking to it? Oh, yeah, can't. No, thanks. Let me know. All right. All right. Let me speak closer. I have to lean over. It's got to point over. All right. So I've got 4 unique water traces. The first water breakthrough occurs because you see a high concentration reaction, so to speak. And then, of course, you know that the breakthrough occurred in the heel. And this correlated very well with the dotted gray line, which is the water cut measurement from the multi-phase meter. And then about a month and a half later, the green zone, broke through with more water and obviously increased. And again, this correlated well with the subsea multi-phase meter. So what that told the operator is that, our multi-phase meter is actually calibrated. Because we know that if you don't calibrate them or you have the wrong PVT, you're going to have erroneous measurements from a multi-phase meter. So they were confident in the tracer results and they were confident in the measurements that were being made by the multi-phase meter as well. Okay. The next case study will be about quantifying how much comes from each zone. And before I go to that case study, I need to explain, how quantification is performed. And we require a shut-in. When you shut in the well, you build up the pressure. At the same time, you also build up a tracer concentration around the vicinity of where the tracers reside in your completion. So it's like this high concentration slug is created. And then when you open the well, the flow will transport those concentration slugs to surface. And typically what you see are bell-shaped curves. They go up, they peak, and then they come back down to steady state levels. Now, because they're all different, that means you have different inflow coming from the different zones. So you can think of this as the peak of the tracer, and it reaches steady state. And because of the rapid decline or decay to steady state, this represents a high inflow compartment or flowing zone relative to the blue zone, which is a smaller decay or decline constant, which takes longer to reach steady state. And this model is actually an exponential fit, and we've seen thousands of flowbacks that are exponential. And when we get a match, we get a decay constant, and then we can calculate the relative flow contribution from each compartment. So just to reiterate, a high decay constant equals a high inflow compartment, and a small decay constant equals a low inflow department. So here's an example. There's an SPE paper based on this as well. It's just modeling the toe of a well. That's all the operator cared about. But it's an extremely long well. It was 45,000 feet long. Now, a POT with a tractor could reach up to 40,000 feet. And they needed to prove to their management that, are we producing any oil at 45,000 feet? So then the tracers were then utilized. So the last 5,000 feet, the 40,000 to 45,000, 21 locations were monitored. And this is the cleanup of all the signals. So you got to shut in, you flow it back, and these are all 21 signals flowed back. So I immediately told the operator that every flow is flowing, even at 45,000 feet, robustly detected. So this is now concentration versus produced volume. All the colors that you see are the actual tracer curves, and the black lines is the model matches for each compartment. And so you can look at, say, compartment 7, and this is the largest producing compartment, so we normalize the decay constant to 1. So the best way to understand this is that at the toe, OS1, this is producing 70% of compartment 7. 18 is at the is one closer to the heel, and that's 0.75 of this compartment, and so forth. So then each compartment, we can calculate the relative percentage contribution from the toe of 1 to 40,000 feet. And surprisingly, in the toe, it was a pretty even inflow. You're talking 3%, but mainly on average 4 to 5% across this toe section of the well. And because of this information, was proven that you can produce at 45,000 feet in the toe. The operator went and drilled 50,000, and then they got the world record now for the longest well in the world. I know there's a lot of gas fields here, so same concept, except the tracers are designed to release the gas only. And now after a cleanup, you get your peaks, and then the models are matched. As you see, there were only 4 signals that came back, but GS3, the blue one, wasn't detected because it was actually installed in a very shaly zone. So there was no production from that zone. And that's verified by the tracers as well and correlated to the logs. So yeah, similar example, but just in a gas field. So let's go to interwell tracers, the ones that you inject in your injection wells, or I call them pumpable. This one is a very simple example where the operator believed there was a connection between injector B to producer AB. And so that was the assumption they had in the model. The reservoir engineer tried to match it, and he or she couldn't, so that's why you get this flat response from the simulator. And the dots are the actual observed tracer concentrations. But once they got tracer information, they actually realized that there was a real connection between injector A and producer AB instead. So they, widened the channel here to allow flow in the model itself, and then were able to match the simulated tracer response with the observed, as you see here. Okay, so the model corrected the previous model that had the wrong assumptions of flow between injectors and producers. But the main value of that study is that they originally assumed there was good sweep between injector B and producer AB. But instead, once this information was proven, the infill wells, they realized that you have a lot of unswept well in this part of the field, and so they went in that part of the field to drill infill wells. Okay? Quantifying connections. This is pretty simple, but very powerful. So we have an injector here where they've injected 150 kilograms, and these are all the connections to all the producer wells. The thicker the arrow or connection, it means there's more tracer mass going to that particular well, like P40. So at a point in time, these are all the kilograms of tracer detected at a particular point in time. If you divide 1.22 kg by 150, you get 0.8% recovery of tracer mass. So this gives you a very visual understanding of what is the importance of connections between this one injector with all the different producers. Okay? This case study is, interesting one too. Although it looks simple, your injector tracer here is detected in producer A and producer B. However, even though this is further away, and I know this is 1 kilometer or 1,000 meters apart, this was only about 200, 250 kilometers apart. So what was interesting was that TB is the time of breakthrough, the first time of breakthrough of the tracer. It took 54 days to reach this producer, which is relatively quick compared to 82 days here. All right. So that's already suggesting that you already have a highway, like a fracture corridor. So let's focus on MO. This is the amount of mass produced at that point in time, 0.14% compared to 3.3%. Now they're small numbers, but this is of order magnitude smaller, right? And also we've calculated the swept volume of only 680 meter cubed versus 35,500 meter cubed. So when I said that this is 1,000 meters apart, if I divide that by 1,000, you'll get 0.68 meter cube cross section of flow flowing through a very small channel, so to speak, or fracture corridor. So the operator didn't know that there was a fracture corridor there, so we identified a geological feature that they were not aware of. And they also would be aware not to drill across this fault there, right? Because you probably get lost circulation, etc. So this is a another very simple but interesting case study. This is a WAG example. Pumping water and then pumping gas, pumping water, pumping gas, to improve the recovery. So we have an injector here, P25. It was injected in 94 and injected once only. P28 is another injector, and we injected 3 different traces in 94, 95, 97. So what happened? There was some gas producing, GOR is constant though, and then it breaks through. And this correlated more with the P25 to this P29 producer. And you see it produced very early, even though a tracer was injected in 94 and there was a tracer injected in 94 as well, in 2 different injectors. But it never came back until much later. So these 3 traces came around the same time, believe it or not, which is, of course, a bit of a surprise. So there must be something in between. There's some geological feature in between this injector and this producer. And what we identified was that there was some attic gas there. It was like a gas cap. And the 3 traces ended up being trapped in this gas cap. And then once they got overfilled, all the 3 traces came out. And that's why they all broke through around the same time. Okay. Now just a couple of slides on carbon capture. So there are traces that are designed only to follow CO2, not just hydrocarbon gas. They only follow CO2 for CO2 EOR or for CCS monitoring. CO2 traces have very low global warming footprint. They're the same, not radioactive. They're non-toxic, and they're there to monitor for the potential of leakage through wells or through the reservoir to surface. And some of you may be familiar with probably the first proper CCS pilot in Algeria. It's called the Insala field. I believe BP, Statoil, which is now Equinor, and Sonatrach are the partners in this. So they had this concern about leakage. So they injected in 2007 3 different CO2 traces. They were only marked the traces, and just be sitting in the reservoir and see if it will ever leak. I mentioned those that special gas sampling tool, that metal tube, that can that's been used for capturing the CO2 in the gas. So the operator were also doing a lot of 4D seismic, of course, to understand what's between the wells. And the interpretation of the 4D seismic is that, oh, there's a channel here, the CO2 plume must be flowing from here to here in this part of the reservoir. But when tracers were injected, they found that the source was actually coming from this injector and not this one. So it corrected the 4D seismic, and they had to change it, of course. And it was after just 5 years that there was breakthrough of CO2 in one of the observation wells, and they had to decommission it and fix the microannulus that were in the well. And I'll put this up because this was an article I found in the JPT in January, where it basically says that, oh, the biggest uncertainty in CCS, one of the biggest one is, where's the CO2 go, the CO2 plume? And it always comes up that you use 4D seismic, but there's no mention of tracers. And, you know, of course, I think, you know, tracers is probably a better way to monitor leaks and also the CO2 plume, and to complement 4D seismic if you continue using it, right? So this is my last slide. Just to summarize the technologies, it is well-proven technology, and as you see, it has many different applications. In producing reservoirs or storage reservoirs, all tracer technology is risk-free. And if you do decide to use both inflow tracers and interwell tracers, there's no interference between them because they're all different. And yeah, so tracers can be used to monitor the inflow, the near wellbore, and between wells. And this is just a quick summary of the information that you can gain from using tracer technology. So that's end of my presentation. So thank you for your attention, and I'm happy for some Q&A.
Doesn't work. Any questions from the floor? Yep.
As an ex-petroleum engineer, how much did you integrate pressure data with your tracer analysis?
A lot. Whenever the operator provides it, they'll often plot the tracer data with the bottom hole pressure, and production data as well, of course, and well test data. Yeah.
Yeah, but did they line up?
Oh yeah, for sure. So when you create a transient, because the tracers follow the flow, if you increase or decrease the pressure or the drawdown, then the tracer will react, and you'll see a disturbance in the tracer response. So it usually correlates very, very closely.
Okay, last point. Which do you consider more accurate, the pressure data or your tracer data?
No, good question. Well, the pressure data is only measuring one depth. Yeah. And of course, it's important information for a reservoir engineer to have that information. But you're adding extra granularity in your well, because yeah, you're getting information from the toe, the mid, or the heel. You're getting more information that you can correlate with production data. Yeah.
Hi. My name is Krowan from PTTEP. I have two questions. One is on the tracer with the reservoir flow. And I'm a geologist, and seen many of your slides that show the flow or the path of the tracers in different wells, in different speed or velocity. I just feel that is it common for you to interpret without putting geological data in it? For example, the fault, channel, direction, that sort of thing? Because for us, that could be detected if you actually integrated that into your model or before you made, any interpretation. That's my first question.
Yeah. All right. So I'll answer that. So, I mean, from my experience, from over a decade, and seeing the traces being detected, often a fault is often missed, perhaps, and then if it does exist, because you do say well testing interpretation, pressure transient interpretation can identify where the boundaries are, but you want to verify that as well, right? And I remember as a reservoir engineer, I did not know if my fault was leaking or completely sealing. If I never detect it between the injector and producer, then you know it's probably sealing. But if you do, then you know there's a leak. But the seismic data will tell you where the faults are, but it won't tell you if it's communicating with the other side. So that's one example. And that case study I showed, they didn't know there was a fault there. And so it's because the trace was detected in that PB well, they looked back at their seismic and had to add that tracer in there, right, as well. So I think the ones that are between wells, you always learn more and find more information about large geological features between the wells. And also, how quickly does it reach there? If it takes a long time to reach a producer or very quickly, it can already indicate to you. If it takes a long time, it means your injection is probably sweeping much better towards that producer compared to one that just produces in a few days or in a month. Yeah, depending on the distance between the wells, of course. Yeah.
Thank you. Thank you for your answer. My second question is about the tracer application in CCS. And you gave an example from Salah. And it showed that actually the leak is actually through the well.
Yeah.
From your experience with tracer in CCS, has there been any leak through geological features like fault or maybe like, the connecting between the seal and the reservoir?
Yes, there is an operator that believes that right now. So they believe it's going through a conductive fault, and the cap rock may have also, let's say, failed in the reservoir integrity, and it may break through to surface. So there are some service companies now providing, we call it soil monitoring. So if it's onshore, then they would drill lots of holes, like about 1 meter deep, and drop in sampling kits, these that 20 centimeter tube I was explaining, into all these wells, and then you'll pick them up, say once every 6 months or once a year, perhaps, and look for the traces, because this operator definitely has a concern of breakthrough through the cap rock now.
Thank you. One small question about the CCUS. Would you consider tracer as one of the MMV, seeing that 4D seismic is, one of the stable kind of MMV technique? Would you consider tracer as another main one?
Yes. Yeah. I mean, 100%. So, I think tracers are not considered because we haven't the domain hasn't educated the industry as well. I think 4D seismic is always the kind of default. But I'm not saying don't use 4D seismic, but the more measurement you have, the better you complement all the other technologies and measurements, interpretation, so you get the best characterization of your storage reservoir or your producing reservoir. But yeah, I really believe tracer information is underutilized in the industry. Yeah, for sure.
Any more questions?
Hi. I'm very fascinated when you had a well with 21 measuring points. How do you differentiate 21 different organic samples that your tracers.
Yeah.
I'm interested in that one.
Okay. Yeah, that's because there are many service providers that have many unique tracers that are all different. So, and it's simple as that. Most service companies will have something like 60 unique oil, 60 unique water, and X number of gas tracers. Just because they're all different, you know where they came from, because you record the tracer ID in the tally of the completion.
Okay.
Yeah.
I understand that, but then from you said they can last 10 years.
Mm-hmm.
Are those little strips that I saw?
Yes, that's correct.
Wow.
Yeah.
Nice technology.
Yeah, and the reason for that is because of I mentioned about that 20 Olympic-sized swimming pools technology where you can get to such low detection limits. Yeah.
Yeah, Michael Pitzer, OPEX. You mentioned also the time span, and as referenced there with the 10 years. When we used some of these in the past, but have you now got the ability to do 10 years of sampling with oil and water as well as gas?
Yeah, I mean, speaking for my company, it is 10 years for the oil, and it's 7 years for the water. But that's upon water breakthrough. So if your well's dry for 5 years and then the water breaks through, then you have 7 years left. So it doesn't, the time doesn't stop ticking until that phase touches the polymer to release. So it's not spent if it's just sitting in oil for 5 years.
And I know you were developing the gas. Mm-hmm. So how many years do you think you've got for the gas?
Gas is relatively new. So at the moment, it's only around 2 years, up to 2 years. Yeah, because it's a much newer technology. It was much more challenging to control the release of a gas tracer out of the polymer. Yeah, but I know that it's going to increase over time. Yeah, for sure.
And you can run all three together, can't you?
Correct. Yeah. You would put them in one screen, perhaps. Yeah. But you can put it across two screens. It just depends on what longevity that you need. Sometimes some operators only want 1 year, and some want 5. So, the longer you want, the more room and more polymers need to be installed. Yeah.
Thank you.
Okay, we have students in the room as well, and they have drank a lot, so let the student ask.
Thanks for presentation. I'm not done yet. My name is Kuranon, a student from Petroleum Engineering, student from Chulalongkorn University. So my question is, when we get the tracer back from in the produced well, do we need to extract the tracer from the fluid before sending it through to the refining process?
Okay, yeah, no. Basically, when it comes to liquid, those bottles are just full of oil and water, and then they're just we just pour maybe 20 mils or 30 mils into a test tube, and then it's just put into a machine to find the tracers. Yeah, so there's a very small volume is required.
So my name is Yuda. I'm from Chula, the same with base, from Petroleum Engineering. So my question is, when you inject the tracer, and I saw some of the table that you inject this specific amount, and the one that being produced is less than the amount that you produce. So it means the tracer is live in the reservoir itself.
Correct.
So is it not ruin the properties of the reservoir itself, or do you gonna do flush the tracer after you do the test? Because if it ruin the properties of the reservoir, it's gonna be quite challenging to make the initial condition of the reservoir.
Yeah, no, good question. No, these when the tracers are qualified, the ones that flow through the reservoir, they're tested and designed not to have very minimal absorption to the grains of the sand. And they're also inert. They will not react with anything. It can be in the reservoir for hundreds of years. So remember, the tracer is following the flow, and it doesn't react. It's a passive tracer. So there's no chemical reaction. It doesn't get stuck to the grains, and therefore it won't change the property of the oil or anything like that, or even plug the permeability, right, between grains, because we're talking sub-nano size. They're molecules. They're much smaller than fines. They're not like sand fines or something like that. Yeah.
Okay, we have one last question. Okay.
Hi. This might be a bit of a stupid question, but anyway. You mentioned dispersion. Are you saying that if you did a time variant injection of a certain frequency or certain wavelet type thing, that you would see the frequency of that sort of change from injector to producer?
Yeah. So just want to clarify, what do you mean by dispersion?
Well, you mentioned it.
Oh, did I? Okay. Yeah. No, I mean, there is. No, I'm actually surprised. I don't normally get this question about dispersion, but I'm very familiar with it. So there are two physics with dispersion of tracer. If you have a very high flowing well, the tracer slug, so to speak, will be violently mixed. So it will come out as a very high peak and then it will decay very rapidly to steady state. But if it's a low flowing well, it will create a laminar flow, and the laminar flow will stretch out that tracer signal, and that's the second order effect. It's a dispersion of the tracer, so it will be very wide signal and will have a very low concentration peak, so to speak. So that's from a perspective of if I'm monitoring a inflow, a permanent tracer well in the well. But of course, dispersion can also occur between the injector and producers as well. But the main physics would be convection. So it's really the flow of water pushing it and sweeping the oil towards the reservoir. So dispersion is not, when it comes to injector producer, the pumpable ones, the dispersion effect is not as significant as if it's convection, meaning that you have the water pushing the oil and the tracer towards the producer. Does that answer your question or not?
Yeah, maybe. No, I was just wondering if there's any benefit for looking at time variant injection, and if the signal was to vary from input to output, could you actually infer any property, reservoir properties?
Yeah, I see what you mean. So the one that you have an injector and producer, you won't really get any, let's say, when you have first breakthrough of a tracer, then you know there's a connection and you know what time and how long it took to break through. And what you'll have, that signal will be a dot, right? And then over time it will go up and up and up. It will peak, and then it will go back down. They're like bell-shaped curves. But to create that curve, it will take months to years to get that curve. So it's a very slow monitoring sort of process, so to speak. But once once it starts declining from the peak, then we can start matching that data with models and so extrapolate what that curve is going to be like, and then it gives you information about sweep efficiency and how much is swept and how effective that sweep is. So yeah, for sure. One thing that comes to mind is that I've seen if you have a two-layered reservoir and you're injecting water, often you'll get like a double peak. So what it will look like is, maybe I'll just try to draw it here. So you'll get a peak that goes up, comes down, it goes up and comes back down. And that signal often I've seen is because you have we have water
Underrunning.
flooding two different zones.
Underrunning, for example.
Yeah. So yeah, there's lots of different sort of information that you can see from signals. But of course, you want to correlate that with your geology and all the other data that you have and all the other measurements. Yeah.
Okay, thank you. I think that's with a sense of time. Let's move on to the next sections. And I think, if you still having questions, we have time at the end, right? I think Edmund's still going to be with us to continue drinking.
Yes.
And
We'll start.
thank you very much for your talk. The tracer technology has been around for so many years, but today you have given us a very good clarities on its applications, and maybe it can be used in the future for Thailand as well. So with that, let me have Kun Rono, our section chairman, to provide the token of appreciations to our speaker today. Okay, now the closing remarks and lucky draw.
And now a few closing remarks before we go to lucky draw. Upcoming for next meeting, we will skip our meeting in April for Songkran season, and we will resume our meeting again in May with upcoming SPE on Thursday, 18th of May 2023, on the subject of decommissioning in Thailand, challenges and opportunities, by Dr. Visarut Tangsunthorn Khan, Director, Petroleum Technology and Operations Supervision Division from DMF. And please also check out our SPE Asia Pacific website with upcoming event. For our neighbor, SPWLA will hold a meeting on the subject Gulf of Thailand drilling project challenges from planning through execution phases by Mr. Jiraj Kamban from Chevron Thailand on Thursday, 30th of March 2023 at Jasmine City Hotel. Please email to bangkok.chapter@swspwla.org if you are interested in this event. And next, very important, there are many ways to get in touch with us by Facebook page, LinkedIn group, and Line official as showing on this screen. And finally, our lucky draw. Can we please have Kun Edmund on the front of the stage again to help us with two lucky winners? Prizes sponsored by SPE Thailand section in appreciation of your attendance here tonight. And the first winner is...
Congratulations to Dave Carter from Valua. Is it?
I think you'll be very happy with our lucky draw.
Well, you're going to sleep well tonight. Yep.
One for you and one for your wife.
For the photo? Yeah.
Yes. Never sleep alone.
Okay, thank you. And the
The second
one.
winner. It's pink.
Yes.
It's pink, so
Okay, this is going to be challenging. Tat Shannon, and then I can't pronounce the rest. Is that you? Oh, okay, great. Congratulations. Win something.
Okay, thank you, Edmund.
and last but not least, feel free to finish your class here in the room If you still want some more drinks, we have arranged special SPE Thailand drinks at the Reservoirs bar on the ground floor lobby level. Tell them you came from SPE meeting and secret password is SPE. They will offer you 2 drinks for one price. Secret password SPE. And now, please give another round of applause to our generous sponsor. Thank you. Thank you for your support to SPE Thailand. Have a great night and see you again in May. Thank you.
You know, the case that you mentioned that